give a warm welcome to Mr. Madhusudan Rapole. Mr. Rapole is the founder and MD of Urja Energy, with professional experience in clean tech solutions for heating, cooling, and ventilation. He has obtained multiple patents in these areas and has played a pivotal role in introducing innovative technologies such as radiant cooling, geothermal cooling, and solar and heat-based cooling. His initiatives have been instrumental in promoting energy efficient and environment-friendly buildings across India. A mechanical engineering graduate, Mr. Rapole has professional degrees from Teli University and Stanford Graduate School of Business. Today, Mr. Madhusudan will share his insights on a pathway to affordable and low energy cooling. So please welcome Mr. Madhusudan.
Thank you, Darshana, for generous introduction, and good afternoon and good evening to you all. What I plan to present is something very simple and very basic. Even a high school student can, I guess, understand this, not some complicated technology. Now, to explain this, I just wanted to show certain temperature readings. A couple of cities I chose, I mean, one was Ahmedabad. And what we notice here is, in summer night, we see ambient temperatures of around 25 to 30 degrees centigrade. This is data from April last year. And we see similar temperatures in winter afternoons, 25 to 30 degrees, right? This was in December. Plus, there is heat of solar radiation also here. But I'm sure all of you agree that we use air conditioning here on a summer night where the daytime temperatures go to 40, 45. Please note, I'm only talking about summer night here. Whereas on winter afternoon, we generally don't use air conditioning. But if you were a student of science and I just gave you two cases, case one, ambient temperature is just between 25 to 30 degrees centigrade, no solar radiation. Case two, ambient temperature between 25 to 30 degrees centigrade, solar radiation is there. And I asked the question, where are you most likely to use air conditioning? Most of you will probably say you're going to use it where it is 25 to 30 degrees centigrade and solar radiation. But that's not how we behave, right? And I can show some more data. This is Delhi, right? Same. This is again in April, nighttime temperatures, daytime temperatures in winter, around the same, solar radiation there, but we use AC here, not here, right? This is October. Now, why? So when we looked into it, why is that? I mean, to some of you, it may be very apparent, but how do we act on this and use this to significantly reduce the energy we consume for cooling? But first, why is this happening? And when we did some thermography, we saw that on a summer night, the temperatures of these surfaces were about 35 degrees centigrade. Right? Even floor, which is not exposed to direct solar radiation, was about 35 degrees, right? And this is not result of a single day's heat being absorbed by the building. This is a result of multiple months of heat being accumulated by the building. So in tropical regions, we know we build our buildings with concrete and steel, unlike many of the Western countries or even most parts of Japan, right? So these buildings, sun comes up, dumps heat, goes away, and these concrete and steel structures absorb and accumulate this heat, which by the time April or May comes, they start re-radiating this heat. And this is what makes us use air conditioning, whereas in a winter afternoon, you would see the temperatures are in mid-20s. Which begs the question that if we were able to somehow flush this heat and bring the inner surfaces to, let's say, below 30 degrees centigrade in mid-20s, then we shouldn't be needing cooling on summer nights, because there's no external heat coming in, unlike a summer day, right? and which is what we used to do. I mean, for most part, if you look at traditional architecture, we had architecture where direct solar radiation was never falling on the walls that the inside of which we were exposed to, right? When you are inside a space, you are only exposed to four walls, ceiling, and floor, right? The temperature of that, because your skin temperature or your body temperature with the clothing is somewhere between 32 to 33. So any surface which has temperature above that will become a heat source to you, which will radiate. A body at a higher temperature will radiate heat to you. Something at a lower temperature will act as a heat sink where you radiate heat to that, which is how the traditional architecture was, right? Where you had a lot of surfaces which were at a lower temperature than your body temperature and could feel comfortable. Right? Now, if you see, you go back here, the current approach, I mean, this approach is also fine, where we are making, how we are trying to see to make it affordable, air conditioning affordable. The approach is how do we make a air conditioner or other equipment cheaper and more efficient? Well, this is one approach. What we are trying to say is if we cool the building, because that is the source of heat, especially in many residential buildings. So much so that India is now developing a second peak in the night, right? There are, I mean, the other day I was reading in Kerala, last year in Kolkata, there were actually blackouts in the night, not during the day, because everybody comes home now, everybody can afford, even at less than, like we said, even at less than 10% air conditioning adoption, there's enough load to basically cause blackouts. So you can imagine what will happen once there is more and more adoption. So what we're trying to say is if we can flush this heat out, and how do we flush this heat out? We embed a network of pipes. Those of you who are aware of radiant cooling should be familiar with this. But unlike radiant cooling, right, where we use a chiller to send cold water at 16 to 18 degrees centigrade, we're just saying send water. That's it. 24 degrees, 25 degrees. You could use multiple heat sinks like cooling tower. Could be a water body. Could be even treated wastewater tank. Right. Just find a heat sink where you can dump this heat so that every day that accumulation doesn't happen. If you're able to flush out, let's say from the end of February, uh, continuing for 3-4 months, that you don't allow the heat to accumulate in the building and keep chipping it off every day. So by the time April or May come, your inside surface temperatures, your space inside surface temperatures remain, if they remain below 30 degrees centigrade, then at least in most part, you can get away with just fan and natural ventilation, okay, which significantly brings down the cost of cooling. Okay. We don't, as many will tell you, and many of you are probably aware, the biggest cost in the air conditioning in terms of operations, is the energy consumption by the compressor. If you are able to eliminate that, we achieve not just the goal of reducing the energy consumption, but also not using refrigerant. In this case, it's just water. Okay. So this was a technology that was recognized by MIT a few years ago. Few buildings where this is implemented and is in the process of being implemented. There's a net zero building in Hyderabad. I'll talk a little bit more about that. The architecture college. These are college dormitories in IIM Raipur, school. So what we feel is such a low energy technology can be very useful for big public infrastructure that is coming up in India, right? We have today, I mean, if we are aspiring to become the third biggest, largest GDP, the country with third largest GDP, we can't say we can't be a society where we say if you go to airport, you will get the air conditioning comfort, but if you go to a bus stand, ISBT or railway station, you have to deal with it. Right? So we are looking at such low energy, low cost technologies being adopted in large part in the public infrastructure spaces like government schools, bus stations, railway stations, government buildings, where basic comfort can be given. Quick run through for a couple of case studies, which will illustrate how this can work. This is an upcoming building in Hyderabad for the Telangana State Renewable Energy Department. Completely, it's a net zero building, net zero energy building. So, of course, whatever energy is being used is being produced by the rooftop solar of 110 kilowatts. And the way this has been achieved is to hybridize structure cooling with radiant cooling, where for most parts of the year, the radiant cooling system works as structure cooling with a cooling tower, basically providing the cooling. Of course, dehumidification is being done using chiller, but the main sensible cooling is being done just using cooling tower. And in monsoon, of course, we require to use both chillers for both systems. But since you have not allowed the heat to accumulate in the summer, the heat being radiated even in June, July would be much lower. Right? So if I allow quickly, so there are two different operating modes. One for summer, where cooling tower is used for, and we call it structure cooling instead of radiant cooling. You will see that the energy consumption is very low, close to about 0.3 kilowatt per ton. In monsoon, since we would end up using chiller, the connected load would be around 0.37 kilowatt per ton. These are, I mean, those who are aware of energy being consumed by a centralized air conditioning system will understand that these are very, very efficient systems. And you can design things this way, then the path to net zero buildings becomes much shorter. A quick case study for the public infrastructure building where there is no air conditioning or very vapor compression based system. This is an upcoming building in Delhi, right next to the T1 terminal. This is the school, and this piping embedded in this, and the swimming pool here acts as the heat and provides warm pool. Please understand that pool will not get hot because you are only removing the heat that is marginally increasing the temperature. So let's say you start this from end of Feb, you would never be removing heat that has reached 40 degrees centigrade in the structure, right? You start removing, you keep this building structure temperature always at 30 degrees centigrade. So the pool remains at about 26, 27 degrees centigrade always, and due to night sky radiation, it cools down. For such a building, if you see, since there's only two pumps which are being used for cooling, your consumption is only 0.9 kilowatt per. And by the way, I'm not saying that this will provide 24 degrees, 50% RH kind of comfort, but this will provide comfort that is sufficient for a building of this kind, the public infrastructure building. So I just wanted to share that technology like this is available. This can be, I mean, there's no patent or anything anybody has. Those interested can, design this, implement it. These are much simpler than most other technologies that are there in HVAC industry. I'll share my contact in case any of you want to know more and want to implement this. So that's it from my end, Darshana. Okay, thank you.
Thank you, sir, for briefing us about a pathway to affordable and low energy cooling.